You're on the starting line, you can feel your heart just hammering against your ribs. The crowd's a blur, right? The only thing that's real is that finish line. But have you ever stopped to wonder what your body is actually doing to get you there? Hey everyone, and welcome to Subject Simplified. Today, we're diving deep into one of the most critical systems for any athlete, the respiratory system. Now, to make sure this stuff actually sticks for your exams, we're going to follow a sprinter, all the way from the starting block to the finish line. We'll see exactly how their body pulls off this incredible feat. All right, let's get into it. So, let me ask you this. A 100-meter dash, it's over in what, 10 seconds? But in that tiny window of time, an elite sprinter's breathing rate can just skyrocket to 60 breaths a minute. I mean, how is that even possible? Well, it all starts with the machinery. To get how that works, we first need to look at the anatomy. I want you to think of your respiratory system as this high-performance breathing superhighway, and it's perfectly designed to get air from the outside world deep, deep into your body. So come on, let's build this machine together, piece by piece. Okay, so picture this. You're following a single particle of air on its big journey. First, it enters through the nasal cavity, where it gets warmed up and filtered. From there, it dives down the pharynx, zips right past the larynx, that's your voice box, and then plunges into the trachea, your windpipe. The highway then splits into two main roads, the bronchi, one for each lung. And then it just keeps branching into thousands of tiny little bronchioles, finally arriving at its destination, these microscopic air sacs called the alveoli. Now here's a really cool part, how your body keeps this whole airway clear. I want you to meet the epiglottis. It's basically the system's bouncer. This little flap of tissue at the top of your larynx slams shut every single time you swallow, making absolutely sure your lunch doesn't end up in your lungs. Pretty simple rule. No ticket, no entry. Of course, this superhighway doesn't run itself. Nope. It's powered by a whole team of elite muscles. You've got your diaphragm, which is the main engine, this huge dome-shaped muscle at the base of your lungs. And helping it out are your intercostal muscles, which are tucked right there between your ribs. They help expand and shrink your chest cavity. These guys are the powerhouse crew that makes the whole machine go. So the key thing here is you have a perfectly designed path and a powerful set of muscles just ready to go. Bang! The starting gun fires. Our sprinter just explodes from the blocks. Now it's time to see what this breathing machine can really do when it's under pressure. So when you're just sitting around, maybe studying, breathing in, or inspiration, as it's technically called, is a pretty chill, passive thing. Your diaphragm and your external intercostals, they just contract gently. But during exercise, it becomes an active, powerful process. Those same muscles contract with way more force, pulling a massive amount of air into the lungs with every single breath. So where's all that air going? It's heading to the finish line of the superhighway, the alveoli. And honestly, the best way to think about these tiny air sacs is like a pit stop for your red blood cells. They roll in, desperate for fuel, get a super fast tune-up, and then race off to the muscles. And this whole pit stop process, it's called gaseous exchange. This is where the magic happens. It's where oxygen from the air you just breathed in jumps from the alveoli into your bloodstream, while the waste product, carbon dioxide, jumps out of the blood and into the alveoli to be breathed out. So the crucial point here is that this swap is what fuels your entire body. And how does this happen so fast? It's just simple physics, really. It's all about pressure. See, in your lungs, there's a high pressure of oxygen and a low pressure of carbon dioxide. In the blood that's arriving at the lungs, it's the exact opposite. And gases, they naturally move from high pressure to low pressure. So, O2 diffuses into the blood and CO2 diffuses out. The big idea? Exercise flips a switch from passive to active breathing, all to power that critical, pressure-driven gas exchange in the alveoli. Okay, so we've covered the mechanics. Now let's talk numbers, because this is where it gets really interesting. You might think you're a big talker, but are you a big breather? Let's actually look at the volumes of air we're talking about here, especially when it comes to athletes. First up, your tidal volume. This is the amount of air you breathe in and out with a normal, relaxed breath. Kind of like what you're doing right now. It's only about 500 milliliters, or half a liter. Not very much at all, right? That's your basic at-rest volume. But this is your vital capacity. It's the absolute maximum amount of air you can possibly breathe out after taking the deepest breath you can manage. For most people, that's around 4.8 liters. This is the number that really matters for an athlete because it's their functional lung capacity for performance. But even after you've forced out every last bit of air you possibly can, there's still some left in your lungs. We call this the residual volume. It's the air that never leaves. Kind of like that one friend who just will not go home after the party's over. And it's really important because it keeps your lungs from collapsing. And this just shows the difference perfectly. I mean, look at that tiny little tidal volume compared to the huge vital capacity. Your total lung capacity is everything combined. Your vital capacity plus that residual volume adding up to about 6 liters. The difference in scale here is just massive. Now, here's why this is so important for sports. An average person has a vital capacity of about 4.8 liters, but an elite swimmer, through years and years of training, they've strengthened their respiratory muscles, the diaphragm, the intercostals, so much that their vital capacity can exceed a whopping 7 liters. The main point to remember is this. While we all have a baseline lung capacity, training can dramatically increase the usable volume, your vital capacity, and that gives athletes a huge edge. Okay, let's get back to the track. Our sprinters halfway to the finish line, their muscles are burning, they're breathing hard, but they're not consciously thinking, okay, time to breathe faster now. So who or what is actually in charge of all this? Well, the answer isn't in their head, it's in their blood. The second you start exercising intensely, the chemistry of your blood starts to change, and your body has some incredibly smart systems in place to detect it instantly. You see, sprinkled throughout your major blood vessels and your brain are these tiny sensors called chemoreceptors. I want you to think of them as your body's chemical detectives. Their one and only job is to monitor your blood, and they're looking for 2 things specifically: rising levels of carbon dioxide and an increase in acidity. When they spot this, they send an urgent message straight to the boss. And who's the boss? It's a part of your brain stem called the medulla oblongata. This is your respiratory control center. It's basically the autopilot that runs the entire breathing show, processing those urgent messages and making instant decisions without you ever having to think about it. So this whole feedback loop is just brilliant, and it's super simple. The chemical detective sense high CO2. They signal mission control, the medulla oblongata. Mission control immediately fires nerve impulses down to the powerhouse muscles, the diaphragm and intercostals, and orders them to contract faster and more forcefully. And the result? You automatically start breathing deeper and faster to get that CO2 out and more O2 in. And our sprinter crosses the finish line. From that very first deep breath on the starting line to the final gasp after crossing it, their respiratory system has been the unsung hero. It's perfectly built, flawlessly controlled, and powerfully adapted to meet the incredible demands of the race. So, there you have it. You now get the structure, the function, and the control of the very system that powers every single move you make. But that does leave us with one more question, doesn't it? Now you know how the oxygen gets to the muscles, but what exactly fuels those muscles to do the work in the first place? We'll have to tackle that in another explainer. If this helps simplify your studies, do us a favor and hit like and subscribe to the Subjects Simplified channel for more content just like this. Thanks for watching.